Hello, this is Vidura. I want to make a correction regarding the test of the E field in an inductor. I had an issue with the optical driver that I used, and actually the pulse was not 200 to 300 nanoseconds, but it was 800 nanoseconds. This was due to a damage of this optical driver which I have used. Then I have tested all my drivers here and all the others are okay. It was a single piece that not responded accordingly to the specifications. So the implication of this, now I have the pulse of actually 200 nanoseconds. The signal is taken on the gate of the MOSFET. There is some ringing due to the wire and discrete components I used. But now you see the E field I will show you now is depending somehow on the duty cycle. It reacts. Also, when I go over a microsecond, it comes to stall and it begins to draw current. The other thing I discovered is that the E field is not always in the core. This depends on the polarity of the connection. When I reverse the polarity, I have the E field on the outer windings of the coil. Okay, now I have reversed the polarity of the coil terminals. And I will put the probe first on the core and then on the winding itself. So you can see now it is on the core. There is still a field, and now I move it on the winding. You can see now the stronger field is on the outside of the winding. Now I will show you another setup. This is a test proposed by Joel Micro. It's a transformer, simple. In this case, it's the ratio is 1 to 2, but it's not important. A blocking diode I will apply, as in the previous test, 200 nanosecond pulse. And in the curve above, you can see the output voltage. I will turn down the frequency a little bit. There is some ringing when the effect termines, but the important thing is this. After the pulse, we get the electric field. Then the electric field is decaying, and there is a self-magnetization in the core in this period, which would give us some excessive energy in this case. We only apply a very short pulse where the current has no time to ramp up to significant values. And then a voltage and a current is induced in the secondary. In the secondary, I have connected a 33 ohm resistor. If I let it open, the voltage goes very high and there's a lot of ringing, so the effect is much clearer with the resistor. It becomes clearly warm, the resistor, there is power dissipated. And on the input there, the meters don't respond in this case because it's very small. I have 8.5 volt now. I will show you the effect when I raise the voltage. Now in 30 volts, and the effect goes much stronger. I have now a peak of nearly 20 volt in the output, and this, as I said, with a load connected. Now I have connected another scope probe over the MOSFET drain source, which will indicate the voltage which is applied to the coil. You can see when the switch turns on, uh, the decay of the voltage is immediately, but when it turns off, it goes up very slowly, relatively slowly, which is